To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.
Hello my dear students, welcome to today's lesson. Today I am going to continue with electromagnetic induction. So we started discussing what electromagnetic induction is in the previous chapter. So you can remember the magnetic cards that are used by employees, then the bank card, credit cards, debit cards, all those use the principle of electromagnetic induction. And the scientist Michael Faraday introduced this electromagnetic induction. And there is the Faraday's law that explains the electromagnetic induction. And thereafter, we discussed an activity and you all saw the activity in the lab where we try to understand what electromagnetic induction is. So when you have a coil and a magnet, when there is relative movement, when the distance between the coil and the magnet varies, there is a change in the magnetic field lines due to that motion. So because of this change, variation in the magnetic field lines, there is an induced electromotive force. And the induced electromotive force gives rise to an electric current. And when we connect the coil to the galvanometer, you all were able to see the deflection in the galvanometer. And then, you all can remember there are three factors that affect the induced electromotive force. What are they? The number of turns in the coil or the windings in the coil, then the strength of the magnet and the speed of the movement of the magnet or the coil. Because here you can either have the coil stationary and move the magnet, or you can have the magnet stationary and move the coil. So either way, there will be a change in the magnetic field lines. Then you will observe the deflection in the galvanometer. And thereafter, I told you all that we can determine the direction of that induced electromotive force using the Fleming's right-hand rule. So that is what we are going to understand now. Direction of the current induced in a straight conductor placed in a magnetic field and connected to a closed circuit. So we are trying to determine the direction of the current. When a straight conductor is placed in a magnetic field perpendicular to the field and moved in a direction perpendicular to both the magnetic field and the conductor, an electromotive force is induced across the ends of the conductor. So here, if you have the magnet like that, here we have the magnetic poles. So let's say north and south. Then we have a conductor perpendicular to that. We have a conductor perpendicular to that. So here you will have the magnetic field lines in this direction. The conductor is perpendicular. So if the magnetic field is this way, conductor is going to be this way. So although I have drawn it this way, it's like perpendicular. And then we need to move it perpendicular to both, to the magnetic field and the conductor. So let's say I can move it up or down. So the movement is going to be either upwards or it can be downwards. So then there will be a current flow. Is that clear, students? So all three have to be perpendicular. The magnetic field, then you can see the conductor is perpendicular to that and the movement is perpendicular to both of those. Then there will be a current flowing through the conductor. So here, this is the magnetic field, that is in this direction. Then we have the conductor perpendicular to that, and the movement perpendicular to both. Then there will be a current generated. So when a straight conductor is placed in a magnetic field perpendicular to the field and moved in a direction perpendicular to both the magnetic field and the conductor, an electromotive force is induced across the ends of the conductor. So that is very important. This part. If the conductor is connected to a closed circuit, a current flows through the conductor due to the induced electromotive force. So only if we connect the conductor to a closed circuit, there will be a current flow due to the induced electromotive force. The direction of current flow can be found using Fleming's right-hand rule. So like I have drawn here, I'll be discussing that again also. You need to use your right hand. You can remember we use the Fleming's left-hand rule. How do we hold the fingers? They have to be perpendicular to each other. So we use the three fingers, the thumb, first finger and the middle finger. Here also they have to be perpendicular to each other. And thumb is going to be the direction of the motion. Then the first finger is going to be the direction of the magnetic field. Then you will get the direction of the current flow. So like I have shown here, north to south is the magnetic field. So first finger is the magnetic field. So that's going to be this way. And let's say the movement is up. You can move it up or down. So now if I'm moving it up, and the conductor is perpendicular. So can you see the direction of the finger? It is going into the board. So that is how you find the direction. The conductor is this way, I told you. So here the current is flowing into the board through the conductor. The magnetic field is from north to south. That is my index finger. Motion upwards, movement upwards, that is my thumb. And the direction of the current flow is given by the middle finger. So this is how we hold it. So it's into the board. That is how we identify the direction. Now let's say if the movement is downwards, still the magnetic field is this way, movement has to be down. So the current, the second finger is pointed towards you. So that means the current is flowing out of the board. Is that clear? That is how we use the Fleming's right-hand rule. So with that, students, I'll move on to the next slide. So here you can see Fleming's right-hand rule. So here you can see, students, now what I explained to you all. Now when the first three fingers, now we have to use three fingers and it has to be the right hand. So you have to understand that, and they have to be perpendicular to each other. So when the first three fingers of the right hand are oriented perpendicular to one another, and the thumb is pointed in the direction of motion of the conductor, and the index finger along the direction of the magnetic field that intersects the conductor, the middle finger shows the direction of the current flowing through the conductor. And here the figure illustrates a right-hand rule. So you have to remember thumb is pointed in the direction of motion. The index finger along the direction of the magnetic field. And the middle finger shows the direction of the current flowing through it. So three fingers. Thumb, direction of motion. The index finger, the direction of the magnetic field, and the middle finger that will point to the direction of the current flow. So motion, field and current flow. That's how you have to remember. Now if we look at the diagram, the figure given to you, here you can see illustrating Fleming's right-hand rule. So here you can see north-south, there are two magnets. So north to south is the direction of the magnetic field. So the field lines are going to be this way. Here you can see the arrow direction of magnetic field that points towards this way. Then we have the direction of motion. The thumb points to the direction of the motion. Then the direction of the current flow is the middle finger. So the field is going to be that way and the motion is upwards. So the current will flow. Now if we consider this conductor, the current is going to flow in this direction. Can you all understand that? So that is how we use the Fleming's right-hand rule. You have to remember that. Now you have to keep in mind, students, since we have learned the Fleming's left-hand rule, that is to find the direction of the force. There is current flow, there is magnetic field, we find the direction of the force related to the direct current motor and all that. But here, this is electromagnetic induction, it is the right-hand rule. Fleming's right-hand rule. Is that clear, student? So then, I'll move on to the next slide. Here we have an exercise given in your textbook. Find and mark the direction of induced current flow using Fleming's right-hand rule in each of the instances given below. So here you can see north and south, north and south. So two magnets are kept and perpendicular to that it is the conductor AB and the motion is shown towards by the arrow, the red color arrow, and here you can see the conductor is connected to the galvanometer. Then of course you can identify or you can determine the direction of the current flow. How do we do that? We use the right hand. The three fingers have to be perpendicular. Thumb, direction of motion. First finger, magnetic field. The middle finger, the direction of current flow. So now here you can see north to south. The field has to be this way. What is the direction of the motion? It is down. So it has to be down like that. Field is this way, motion is down. So if you consider the conductor AB, what is the direction of the current flow? It's going to be like this, inwards. So it will flow from A to B. So there A to B. Or here they have said find and mark. So if you are to mark the direction of the current flow, it's going to be that way. I have written and marked as well. A to B. Is that clear? Then the second one. Now here, look at the instance. What have they changed? The magnets. Now the north is here, south is there. So the field is going to be that way. But the motion is also down. That's the same as before. So field this way, motion down. The middle finger points towards you. So the direction is going to be B to A. So here it is going to be B to A. Now like in the previous exercise, he also tried to relate the change and the direction of the current flow. What has changed? Only the direction of the magnetic field. When one factor changes, the direction of current flow changes. Earlier it was A to B, now it is B to A. Still the motion is in the same direction. Is that clear, students? So then, if we look at the third instance, now again you can see north to south. Here look at the diagram, north to south. So the field is going to be north to south and the motion is upwards. So if it is upwards, what is the direction of the current flow? It's from B to A. So here it is going to be B to A. Is that clear? So now if you compare these two, the magnetic poles are the same. North here, south here. Here the motion is down, here the motion is upwards. So B to A. Earlier it was A to B, now it is B to A. Then the last one. You can see here again the field has changed. Similar to this one, north to south. So the index finger has to be towards that direction. Motion is upwards. So look at the middle finger. It is that way. So there the current flow is going to be from A to B. Now if you compare these two, can you see? The magnetic field is the same, but the direction of the motion has changed. So the direction of current flow has changed. Compare these two. What is the difference? Direction of motion is the same, but the magnetic field is different. Here north to south, here north to south. So the direction of current flow is also in the opposite direction. And if you compare the first and the fourth instances, direction of the current flow is the same, A to B. So there are two factors that have changed. The magnetic field is also changed and the direction of the motion is also changed. Now here also students, you all have to remember, there are three: the motion, magnetic field and the direction of the current flow. When two factors change, both factors are changed simultaneously. The direction of the current flow doesn't change. But if you change the one factor, then the direction of the current flow changes. So you have to understand that as well. Is that clear, student? So then I'll move on to the next question. So there is the other question given here. Find and mark the direction of the induced current flow using Fleming's right-hand rule in each of the instances given below. So now that you have understood how to do this, I'm sure you all can do it on your own first, and then we can mark it on the diagram. So how do we do the fifth one? Now here you can see the way they have given the diagram is different. What is the difference? The magnetic field is given, the motion is shown as before. Only thing, you don't see the conductor, but you all know the conductor should be perpendicular to the magnetic field. It's only marked as a circle there. And here there is no galvanometer, there is no external circuit. We need to find the direction of the electromotive force, induced electromotive force. So what do we do? Again, right-hand rule, north to south, this way, motion upwards. So the field, the current is going into the board. What is the symbol? Here we put a cross and a circle. Current goes into the board. You all can remember those symbols. Dot and a circle when it's flowing out. Cross and a circle when it's flowing into the paper or the board. Then, if we look at the fourth instance. Now here the field has changed. So field is this way, motion upwards. So the middle finger points towards you all. So that means current is flowing out of the board. So here it's going to be a dot and a circle. That's how we indicate the current flow coming out of the board. Then the seventh one. Again the field is north to south, this way. Motion is downwards. So it's going to be this way. So the current flow is out of the board. Is that okay? So it's going to be again out of the board. The last one. Field is going to be this way, the motion downwards. So if you look at the direction of the middle finger, it's pointing into the board. So there it's going to be a cross and a circle. Now here also you can identify the relationship. In these two, the field is the same, direction of motion is opposite, current flow is opposite. If you take these two, again the direction of magnetic field is the same, but the direction of motion are opposite. Therefore, the current flow are opposite. Now these two, motion is in the same direction, but the magnetic field is in the opposite directions. So the current flow is opposite. Here also, the direction of the magnetic field changes, motion is the same, so the direction of the current flow changes. If you take these two, both factors change, so the direction of current flow doesn't change. If you take the sixth one and the seventh one again, both the magnetic field is different and also the motion is different. So the direction of the current flow does not change. So here also you have to understand, when you change the direction of only one factor, the direction of current flow changes. But if you change the direction of both the factors simultaneously, then the direction of current flow doesn't change. You have to understand that, student. So with that, we will move on to the next slide. So here we look at the applications of electromagnetic induction. So under that, we have the first application, alternating current dynamo. Now when we discussed electromagnetic induction, I told you all, you can remember, when we use different sources to produce electricity, oil, nuclear power, even hydropower, I mentioned the turbine to you. So when the turbine rotates, there is electricity generated. So there is rotation, there is a magnetic field, that is what happens in the turbine. An electromotive force is induced and electricity is generated. So alternating current dynamo also does a similar function. You are familiar with dynamo. In the household also, sometimes as an alternate current source, we use the dynamo. In industries, households, schools, we use the dynamo. When there is no electricity supply, we use the dynamo. So there it is the alternating current dynamo. So you all know what alternating current and direct current are. Alternating current, current where the direction of current changes with time. AC current. That is the current we get to our households. You can remember 230 volt, 50 hertz alternating current. So that is what is generated by the dynamo. So dynamo in a hydropower plant generates the alternating current, and that is what is applied to the household. Or if you take a bicycle dynamo, that also generates alternating current. So now if we look at it, alternating current dynamo, figure shows an alternating current dynamo. A rectangular coil ABCD consisting of a number of turns of an insulated copper wire wound around it is connected to an axle that can be rotated around its axis. A strong magnetic field is applied across the coil using a north and a south pole placed on either side of the coil as shown in the figure. Terminal A of the coil ABCD is fixed to a coaxial copper ring P and the other terminal D is fixed to another identical copper ring Q. P and Q are known as brushing rings. So here this term coaxial copper wire. When we say coaxial copper wire, that means it is a copper wire that has a metal covering that cuts out signal interference. So that is a coaxial copper wire. So this is a coil ABCD that is fixed to a coaxial copper wire ring P and the other terminal is fixed to the terminal D. I'll move to the diagram and then we will come back to this slide. So here I have the diagram. Now this is what is shown. You can see the permanent magnet, north and south poles, that was also mentioned. Then here you can see the coil ABCD. Now they have drawn that in two different colors. So it's so easy for you all to identify it when it rotates. So one side is blue color, the other side is red color. Now you can see the red color side, that is the CD side, is connected to the ring Q, that is the coaxial copper ring. Then you can see there is another ring P that is connected to the side AB. Then there are carbon brushes. You can see this. These are the carbon brushes X and Y. They are in contact with the copper rings. So those are known as the brushing rings. The copper rings are known as brushing rings, and these are the carbon brushes. Carbon brushes are connected to a galvanometer. So how is this going to work? There is the magnetic field. So first index finger is the magnetic field. So it's going to be this way. Now this particular coil is going to rotate. Now here you can see it's shown as axis. So it's going to be the axle that is going to rotate. Because there should be motion, no? Then only the magnetic field lines will be cut off. So here you can see direction of the rotation of conducting coil. So if the direction is shown this way, that means it's an anti-clockwise direction. So this coil is going to move in an anti-clockwise direction. That means the side AB is going to move up, CD is going to move down this way. So if we consider the side AB, if we apply the Fleming's right hand rule, then you can see magnetic field is from north to south this way. AB will move upwards. So the current will flow into the conductor AB, that is from A to B. At the same time, if we look at the side CD, again magnetic field is the same, but the motion is going to be downwards. Why? It's a counterclockwise or anti-clockwise rotation. So motion downwards means current flows out. So through this conductor, current will flow in the direction AB, CD. When they flow that way, you can see A, B, C, D. D is connected to ring Q, then that is connected to Y, that is connected to the galvanometer. Again on this side, BA is connected to P, that is connected to carbon brush X. So there will be a current flowing through this coil. Therefore, there will be a deflection in the galvanometer. That is how the electromotive force is induced. Because of that, electricity is generated. So for you all to use the right hand rule only, they have shown this. We have applied for both AB and CD. So you know there is continuous rotation. Here in the diagram they have said application of Fleming's right hand rule to AB part of conducting coil. So again there you can see force, current and magnetic flux. Why do they say magnetic flux? Because there has to be a variation in the magnetic field line. Flux means variation. So that's why it's indicated as magnetic flux. Is that clear, student? So this is how a current is induced. That is induced current in a conducting loop rotating in a magnetic field. So this is basically the function of a dynamo. So like I said, I'll go back to the previous slide where we looked at the introduction. Now you can understand this. So figure shows an alternating current dynamo, a rectangular coil ABCD consisting of a number of turns of an insulated copper wire wound around it is connected to an axle that can be rotated around its axis. So that is what was shown here. You have the wire coil and this is the axis, and that axis is being rotated due to the axle. Then a strong magnetic field is applied across the coil using a north and a south pole placed on either side of the coil as shown in the figure. You saw that as well. Terminal A of the coil ABCD is fixed to a coaxial copper ring P. Coaxial copper ring P. And the other terminal D is fixed to another identical copper ring Q. And P and Q are known as brushing rings. So you have to remember that. Now you all can understand the explanation given here. we have discussed this diagram also. So with that, students, I will move on to the next slide. So there are two brushes X and Y made of carbon are mounted in such a way that they brush against the brushing rings. So I explained that with the diagram. You can understand that. Here also the diagram is given. So you can see X and Y are the carbon brushes. So they brush against the brushing rings. So that is something you need to understand there, students. So those are the two brushes X and Y made of carbon are mounted in such a way that they brush against the brushing rings. So you have to be familiar with these terms. The coil is connected to the external circuit which consists of a center zero galvanometer through the brushes X and Y. So here we use a center zero galvanometer. The part consisting of the coil ABCD, brushing rings and the axle is known as the armature. So here also there is an armature. Now here it consists of the coil ABCD, brushing rings and the axle. All together is the armature. Then you can see here, since the arms AB and CD of the coil intersect the magnetic field across the coil, when the coil is rotating, an electromotive force is induced across these arms. So you can remember initially we understood that when the magnetic field is stationary, the coil has to rotate. So here also the coil ABCD rotates. Then it intersects the magnetic field. So when there is a magnetic flux only, a variation in the magnetic field only, electromotive force will be induced. That is what is explained here. Since the circuit is closed, a current passes through the arms AB and CD of the circuit, and the direction of this induced current can be found using Fleming's right-hand rule. So you all know what to do here. So the field is from north to south. If you consider the conductor, the side AB, we did that before also. Direction of the rotation is the anti-clockwise direction. So AB moves upwards. Magnetic field that way, the index finger, thumb points to the motion. So current will be into the conductor. That is in the direction ABCD. Is that clear, student? So that is how current will flow. So ABCD, then to Q, then from there Y through the galvanometer to X, P, again ABCD. In that way, the current will flow. Is that clear, students? So we can find the direction of the current flow using the Fleming's right-hand rule. So with that, students, I will move on to the next slide. If the coil is rotated in an anti-clockwise direction. So this is what I explained to you all. Anti-clockwise direction as shown in the figure. According to Fleming's right-hand rule, the induced current flows from A to B since the arm AB is moving up, and from C to D since the arm CD is moving down. That is what we determined before also. Since both currents through the arms AB and CD are induced in the same cyclic direction, a current flows through the coil in the direction ABCD. So the current flows through the coil in the direction ABCD. Then the current flow across the galvanometer in the external circuit is from Y to X. That also I explained to you all. Y to X. It is from Y to X. In the galvanometer, it is in the direction Y to X. Then the galvanometer indicator deflects to the left. So if it is from Y to X, it deflects this way. It deflects this way, left side. Deflection is, or we can show it this way. If the 0 is here, the deflection will be towards this side. Center zero galvanometer, no? So towards the left side. Because the current flows from Y to X. Is that clear, students? So then I'll move on to the next slide. Figure shows how the induced voltage in the coil varies with time when the ABCD coil shown in figure is rotated anticlockwise in the magnetic field. Now this diagram figure shows how the induced voltage in the coil varies with time when the ABCD coil shown in figure is rotated anticlockwise in the magnetic field. The upper part of the figure shows how the coil, that is the armature, rotates in the magnetic field. Now I'll explain the figure to you all. Now here you can see, students, the pink color lines, that is the magnetic flux. So if you have your Fleming's right hand rule, the index finger has to point that way. Then what you see as these blue color arrows, those are the direction of the motion. Now here, when the armature is this way, it is perpendicular to the magnetic field and it is rotating in the anticlockwise direction. You can see this blue color arrow, the rotation is in the anticlockwise direction. So then when it is like this, it's going to rotate this way. So the CD arm is going to move that way. So the force is acting towards this direction. While the AB part is going to go that way. So the force is this. Now in this instance, how are these lines? Now you can see the magnetic field line is in that direction, while the motion is in this direction. So are they perpendicular or parallel? In this instance, they are parallel to each other. Now here they are parallel. Now for this electromagnetic induction to happen, the magnetic field and the motion have to be perpendicular. But here it is parallel. Then at this instance, there will be no induced electromotive force. Is that clear? So there will be no induced electromotive force. There will be no EMF. But if you look at the next diagram, B. Now the armature was in this position. It has rotated to this position. Now still the magnetic fields are in the same direction. But you can see the motion. AB side is going to move up. The CD side is going to move downwards. Now what are the directions? Magnetic field lines this way. If we consider AB, the thumb is upwards. So how will the current flow through AB? In the AB direction. The same way if you consider CD, movement downwards, field is from in this direction, so current flows out. So the direction of current flow is going to be ABCD and the armature rotates in the anti-clockwise direction. Now look at the graph given here. Now I told you all these two are parallel. The motion and the magnetic field are parallel. So because of that, you cannot apply the Fleming's right hand rule, and also when the motion and the magnetic field are not perpendicular, then there is no induced electromotive force. So that is what is shown in the graph. Induced electromotive force. Vm. Electromotive force M. V is potential. So you know this is denoted as Vm because the electromotive force is induced due to the fluctuation in the magnetic field. So this is the positive value. Here you can see the negative value, and that is the degree, that is the 0 degree is the degree of the armature, the angle of the armature. This is the initial position or the coil, you can say. Coil ABCD initially it's considered as 0 degrees. There is no EMF, no induced electromotive force. 0. Why? The motion and the field are parallel to each other. But from there, you can see it's going to slightly move that way. So there is a magnetic flux. Then you can see the electromotive force that is induced increases gradually. And when the coil has rotated by 90 degrees from this position to this position, it was here like that. It has rotated by 90 degrees. So at that instance, you can see the force or the motion and the magnetic field are perpendicular. There is the maximum induced electromotive force. So students, you all can see you have to compare the coil with the induced electromotive force. So there you can see now in this one, when the motion and the magnetic field lines are parallel, there is zero electromotive force. So here you can see 0. In position B, when the motion and the magnetic field lines are perpendicular, there you can see the maximum induced electromotive force. So that is the second position. Here you have to remember the armature or the coil ABCD, that is part of the armature, rotates anti-clockwise. And the current flow you can remember, earlier also we discussed Y to X. So then, if we move on to the next position. Now here you can see 0 initial time, then T divided by 2, 4, that is quarter turn, T divided by 2, half a turn, then 3T divided by 4, 3/4 turn, and a full turn T. That is what is shown as T there. So here this is the time and the angle is also shown to you all. Now the coil has rotated by 180 degrees. It was here like this. So you can see A and B were down, C and D was up. Now after 180 degrees, AB is up, CD is down. So there also you can see the arrow, blue color arrow, that is parallel to the pink color lines. So this is the direction of the motion. This is the magnetic field lines. So they are parallel to each other. So because of that, there is no induced electromotive force. So here again you can see there is no induced electromotive force. Now if you look at the curve properly, you can see initially this position rotates and again this way. So there, while it is perpendicular, then the electromotive force is maximum. When they are parallel, the electromotive force is 0. In between, there is a gradual change. So there is a maximum electromotive force. Then, continuously, if you look at the position D, continuously the coil is going to rotate. Now, if you look at the side, now CD or DC is going to move upwards. The magnetic flux is this way. So the current flow through CD is inwards. Now earlier current flow through CD was outwards. Now CD, or it is in the direction DC. Here it was CD. Now it is DC. Then on this side it is BA. So the current flow is going to be DCBA now. Earlier it was ABCD, now it is DCBA. So what has happened to the direction of the current flow? It has changed. So here you can see when the coil goes from position C to position D, you can see here from 0, the electromotive force increases in the opposite direction. So it is minus Vm, minus potential. Then when it goes from this position D, that is the 3/4 turn, 270 degrees, to the complete turn, 360 degrees. Again you can see the magnetic flux is in the opposite direction for the, as like in opposite to the previous case where you have the curve in the negative region. But again, the electromotive force decreases and reaches 0. When it is parallel, the motion and the magnetic field are parallel, again it reaches 0. So you can see these positions B and D, when the motion is perpendicular to the magnetic field lines, the induced electromotive force has a maximum value. But when they are parallel, the induced electromotive force is 0. And also the induced current, the direction changes. Initially this direction, positive current, then negative current. So what is this type of current? It is an alternating current. So initially also we said alternating current dynamo. The direction of the current changes with time. So this is actually facilitated by, I'll go to the previous slide where you can see the diagram clearly. This movement is facilitated by these complete rings, which are called the brushing rings. So even when the coil rotates, the ring also is complete. So always ring Q will be in contact with Y, ring P is in contact with X. So when current flows from A, B, C, D, it comes to Q, Y and towards X. But after 180 degrees turn, then current flows from DC, BA. So DC, BA, from A the current flows to P and then to X, from X to Y. That is possible because the rings are complete. So you have to understand that. Now if you remember students, you have understood the function of a direct current motor. The components are somewhat similar because you remember the north and south pole, the coil, but there were split rings. Here there are complete brushing rings. So in this instance, now these complete rings, those are the brushing rings, facilitate the flow of alternating current. Is that clear, students? So you have to keep that in mind. So with that again, I'll go back to the slide. This is what we were discussing. So you have to remember the positions of the coil and why in certain positions the potential is 0 and it has potential maximum. Induced electromotive force. So the dynamo produces alternating current. Is that clear, students? So with that, I'll move on to the next slide where the discussion is continued. So here also, like I explained to you all, since the arms A, B and C, D are moving parallel to the magnetic field when the rotating coil is in position A. So this is what I already explained to you all. You can see A, B and C, D are parallel to the magnetic field when the rotating coil is in position A. The conductors do not intersect the magnetic field lines. Therefore, an electromotive force is not induced in the arms A, B and C, D. Therefore, the galvanometer does not show a deflection. So, that is what I explained with the graph. That is this particular position here. This first position A. While the coil is rotating from position A to position B, the rate at which the field lines are intersected by the coil increases. Therefore, the galvanometer deflection increases accordingly. So, from here to here. All these are what I explained to you all, but with the information given on the slide. So, then, if we move on to the next one, now here it is position B. So, you can see there, position B is the position of the coil after the coil has rotated by 90 degrees from position A. At this position, the field lines are intersected perpendicularly by the coil in the upward motion of AB and downward motion of CD. then a current flows in the direction ABCD. That's important. Current flows in the direction ABCD. So, you can remember that. We use the Fleming's right hand rule and we determine the direction of the current flow. Is that clear, students? So, ABCD direction, causing a deflection to the left of the galvanometer. To the left of the galvanometer. Is that okay? So, then I'll move on to the next slide. So, here you can see. This is for the third position. While the coil is moving from position B to position C, the coil is rotating from 90 degrees to 180 degrees. And the electromotive force during this period keeps decreasing. The electromotive force keeps decreasing and becomes 0 at position C. When the coil rotates from position C to D, the coil is rotating from 180 degrees to 270 degrees. So, it's B to C and then C to D. During this time, AB moves down and CD moves up, intersecting the field lines. Using Fleming's right-hand rule, one can find that the induced currents flow from D to C and B to A. Therefore, the induced current flows through the coil. Induced current flows through the coil in the direction DC BA. So, I explained that to you all. This causes a deflection to the right-hand side of the galvanometer. Deflection to the right-hand side of the galvanometer. So, I explained that to you all in the previous diagram also. Here, if you try to apply this for DC. DC, the field lines are this way, motion is up. So, the current flows in the direction DC. If you apply for BA, again the field is this way, motion is down, current flows from B to A. So, that is what I explained to you all before also, but just to confirm that to you. Right. So, that is what happens when the coil moves from C to D and again D to C. The movement, deflection of the galvanometer is in the opposite direction, towards the right. Here it was towards the left, then here it is towards the right. So, alternating current. Then, with that, we'll move on. So, here also the explanation continues, the same diagram. Since the induced electromotive force becomes maximum in the horizontal position. So, this is important. Induced electromotive force becomes maximum in the horizontal position of the coil. When the field lines are intersected perpendicularly, that is in positions B and D. When plane ABCD of the coil is parallel to the magnetic field, the current flow becomes maximum at those positions. The plane of the coil ABCD is parallel to the magnetic field. So, here you can see that. Now, this plane is parallel, but the motion is perpendicular. So, here you can see the magnetic field is also this way, the coil is also this way. So, they are parallel, but the motion is perpendicular. That is when you get the maximum electromotive force. Same here. The coil is parallel, but the motion is perpendicular. So, maximum electromotive force, but in the opposite direction. So, there, if I read that again, since the induced electromotive force becomes maximum in the horizontal positions of the coil when the field lines are intersected perpendicularly in positions B and D. When plane ABCD of the coil is parallel to the magnetic field, the current flow becomes maximum at those positions. So, here the current flow becomes maximum at those positions. The induced electromotive force becomes 0 for vertical positions of the coil, that is positions A, C and E. So, vertical positions A, C and E, the induced electromotive force is 0. positions B and D when the plane of the coil is parallel but the force motion is perpendicular. Then there is maximum electromotive force. In between, there is either gradual increase or gradual decrease. So that is the alternate current generated by the dynamo. Is that clear, students? So that is how the alternate current is. So with that, students, I will move on to the next slide. So here also we have the same diagram. Now here you can understand when the coil rotates continuously in this manner. Coil rotates continuously in this manner. It can be seen that the current flow in the external circuit alternates its direction. We can see that the direction of current flow oscillates periodically since the galvanometer deflects to the left in B, becomes 0 in A, C and E, and deflects to the right in D repetitively. So this is going to be an alternate current. Alternates its direction. That is, the current changes its direction in each half cycle during one complete cycle of rotation of the coil. So in one complete rotation of the coil, the current alternates its direction. The variation of this alternating current or the induced electromotive force with time can be represented by a sinusoidal wave as shown in figure. So very important, sinusoidal wave. What is a sinusoidal wave? You can remember when we have a graph like that. A graph that goes like that is a sinusoidal wave. So here you get the positive electromotive force, negative, positive, like that. The direction is alternate. So this is an alternating current. Alternate current. You will have the time and that is going to be the current produced by the induced electromotive force. So the sinusoidal wave means this type of wave. Is that clear? So the same wave is shown here also. Here you can see this is the sinusoidal wave. Is that clear? So with that, we'll move on to the next slide. So again the same diagram, I have explained this to you all very clearly. When the plane of the coil is parallel to magnetic field, the EMF becomes maximum in plus or minus direction. This part is important. When the plane of the coil is parallel to the magnetic field, the EMF becomes maximum in the plus or minus direction. And when the plane of the coil is perpendicular to the magnetic field, EMF becomes 0. So you can't decide based on the plane of the coil. You have to consider the Fleming's right-hand rule. The motion, magnetic field and the current has to be perpendicular. So when the plane of the coil is parallel, motion is perpendicular. This is perpendicular to the magnetic field. But when the plane is perpendicular like that, then of course motion is parallel. So that is why here the electromotive force is 0, here the electromotive force is maximum. Is that clear, students? So you have to keep that in mind. So that is how the electricity is generated by a dynamo. And the dynamos are alternating current dynamos. And the phenomenon is the electromagnetic induction that was initially introduced by Michael Faraday. I am sure you all have understood up to now. So with that, students, I am going to end this chapter, and in the next chapter I will be discussing another application of electromagnetic induction, that is the moving coil microphone.
To watch these important lessons, subscribe to DP Education's YouTube channel right now. Click on the bell icon to stay updated on the latest lessons. Sri Lanka's largest free online school, DP Education.